Dear participants, the EFFECT team warmly welcomes you to this second module on designing and implementing randomized controlled trials. Successfully completing this module will allow you to understand the concept of RCTs, understand fundamental aspects underlying RCTs such as randomization or the concepts of treatment and control groups, and learn more about ethical aspects of RCTs. Therefore, this module has two purposes. The first one is to provide you an introduction into experimental settings, and the second one is to introduce you to the interpretation of experimental results. Dear participants, welcome to submodule 2.1, in which we will start to introduce the concept of RCTs. We will introduce this concept via a case study that we already saw in module 1. Which is the case study based on the article A Summary to Communicate Evidence from Systematic Reviews to the Public, Improved Understanding and Accessibility of Information, a Randomized Controlled Trial. Santesso and colleagues found that how evidence is communicated has an impact on how well it is understood. But today, rather than concentrating on their findings, we will analyze this study from a rather methodological lens. To do so, let's have a more detailed look at their research question. The research conducted by Santesso and colleagues aimed to analyze whether the new format improved the public's understanding of harms and benefits of a treatment. They aimed to allow citizens to better understand the impact of vitamin C on the common cold and its underlying evidence using either the plain text summary format on the left or their new format on the right. In the article, Santesso and colleagues write that they evaluated whether the new presentation improves understanding about the benefits and harms of an intervention and the confidence in those effects, whether it improves the accessibility of the information, and whether it is preferred over other versions by patients and the public. We can therefore see that Santesso and colleagues search for causal effect by the choice of the words. They talk about the new presentation improving the understanding. The presentation is therefore supposed to have an impact on people's understanding, and we actually analyze a causal effect. This allows us to draw a first conclusion on causal effects estimation. Santesso and colleagues wanted to estimate a causal effect, and they use an RCT to do so. Therefore, we can conclude from this that an RCT can be used to estimate causal impacts. Dear participants, welcome to submodule 2.2, in which we'll continue to introduce the concept of RCTs by having a more detailed look at the experimental strategy used by Santesso and colleagues. The 193 participants participating in the study conducted by Santesso and colleagues have been randomly allocated to two groups. While the first group was exposed to the old format of the plain language summary, the PLS format, which is the format on the left, the second group was exposed to the new format, which is the format developed by the researchers, presented in the study, and depicted on the right. Therefore, we can derive an important characteristic of an RCT. In an RCT, participants are randomly allocated into two groups, which follow a different path of the study. The main result established by Santesso and colleagues was that their new format led to a better comprehension of the evidence. Indeed, 53% in the group which received their new PLS format understood the evidence, whereas only 18% in the group which received the old PLS format understood the evidence. But how can we be sure that this impact actually came from the treatment, meaning from the new format? Let's reflect on the groups. The participants were randomly allocated to their respective groups, so there should be no difference between the individuals in the groups, at least on average. And therefore, any difference which would occur between the groups at the end of the treatment should come from the program itself, which means that we have just established a causal impact. Let's put it otherwise. If we have two identical groups, and one of these two groups undergoes a treatment, while the other group does not, if the two groups are different at the end of the study, this means that the treatment had an effect. To be perfectly rigorous, The difference can be unambiguously attributed to the treatment if we are sure that the treatment group and the control group were comparable before the treatment occurred. We suppose that this is the case in this context, but we would need to verify this to be perfectly and 100% sure. Dear participants, welcome to submodule 2.3, in which we'll have a small look at where RCTs come from, more precisely, their origins in medicine. Let's come back to evidence-based medicine, which emerged in the 1990s in the United Kingdom and used methods such as RCTs to evaluate the effectiveness of treatments and medications, which means that the methods that we use today in economic education research to evaluate the impact and the effectiveness of programs actually come from medicine. RCTs were generalized to evidence-based policies in the UK and the USA, particularly in the social sector and the education policy. And nowadays, RCTs are seen as the gold standard to obtain evidence, not only medical evidence, but evidence in an even broader sense. Dear participants, welcome to submodule 2.4, in which we'll start to have a look at a first RCT-based case study. This case study is based on the article The Effects of Computer-Assisted Adaptive Instruction and Elaborated Feedback on Learning Outcomes, a Randomized Controlled Trial, published by Dr. Kati Terbeke, Professor Christoph de Witte, and Professor Wouter Schelfhout, who found that no additional learning gains could be observed with adaptive instruction and elaborated feedback. Again, rather than focusing on their findings, let us reflect on how Dr. Terbeke and colleagues were able to draw this conclusion. To do so, put yourself in the shoes of the researchers. If you want to try to evaluate a program or an intervention or a policy, you might have many different factors that might explain the results you find. And the results in this case does not necessarily mean that the program is effective. If a program is not effective, this can be a result and a valid result as well. But no matter what your results are, many different factors might explain them. The first one would be that the program was indeed effective or not effective depending on your result. But other factors that might also explain the results could be that the tested students have slept well or slept badly the previous night, the tested cohort was particularly strong, or the tested cohort had a great economics teacher who covered the material with them. So as you can see that without a proper randomization, it is very difficult to unambiguously attribute the observed effect to the program, as you have many different factors that might influence the results in this or that direction. And to do so, we need a causal strategy. We need to be sure that the effect that we observe actually came from our intervention, from our policy, from our program, and not from any other correlational factor that might also influence the results. Dear participants, welcome to submodule 2.5, in which we'll continue our RCT-based case study by having a more detailed look on the empirical strategy used by Dr. Terbeke, Professor de Witte, and Professor Schelfhout. What Dr. Terbeke and her colleagues actually did was that based on a sample with 46 schools and 118 8th and 9th grade classes, they stratified based on the educational network, participating grades, school size, and the education tracks offered, and then assigned the participants to 3 experimental conditions or 3 treatment conditions and 1 control condition. Let's have a look at the 4 different conditions to which a study participant could be assigned. First, a study participant could be assigned to the control condition, which means that they simply did not participate in the financial education program. Then, a study participant could also be assigned to the first experimental condition, in which they received the same learning path with elaborated feedback. If now a student was assigned to the second experimental condition, they received an adaptive learning path with elaborated feedback. And if they were assigned to the third experimental condition, the students followed an adaptive learning path with verification feedback. In this context, a verification feedback was simply this task was solved correctly or incorrectly, whereas an elaborated feedback was more detailed. Dear participants, welcome to submodule 2.6, in which we continue our RCT-based case study. Today, we reflect on the question why we should conduct a randomization. If the treatment and control groups do not significantly differ from each other at the beginning of the intervention, we can actually follow two different paths of the same kind of participants. But otherwise, an RCT is nothing else than two different states of the world. The control group gives us the state of the world if we do not implement the policy or the intervention, while the treatment group gives us the state of the world that occurs if we implement the policy or the intervention. And if now these two states of the world are different, we can actually conclude that our policy or intervention has an effect. This is visually summarized on this slide. The treatment group allows to show the path of the group who followed the intervention, whereas the control group allows to simulate what the path would have been if the group had not followed the intervention. This is only possible because the two groups are comparable at the beginning of the study. If this is given, then an RCT actually allows us to simulate these two states of the world, the treated state of the world and the control or non-treated state of the world. Dear participants, welcome to submodule 2.7, in which we will discuss the difference between randomized controlled trials and difference in differences. At this point, we will not yet detail what the difference in differences is, but it is important that you understand the difference that exists between an RCT and a Diff-In-Diff setting. What is a difference in differences? A difference in differences is actually the statistical or econometric technique used to interpret or to compute the treatment effect of a randomized controlled trial. But not every study using a difference in differences approach is automatically an RCT. For a study using difference in differences to be a randomized controlled trial, it is crucial that the treatment and control group have been created through randomization, while creating two groups which are more or less comparable at the onset of the study, which means before the intervention. Difference in differences can also be used outside of randomized contexts. In this case, these studies are called non-randomized difference in differences, and we will discuss them in Module 3. What you should take away for now is that RCTs often use difference in differences, but not every difference in difference is automatically an RCT. Randomization is crucial and makes the difference between an RCT and a Diff-In-Diff. Dear participants, welcome to submodule 2.8, in which we'll start to learn how to set up an RCT. Let us start from what we call the population of reference. The population of reference is defined through general criteria, and the sample will need to be as representative of the population of reference as possible. Imagine, for instance, that you want to test a treatment effect of a financial education program on students enrolled in schools in the Asturias region in Spain. However, there are many schools in the Asturias region in Spain, and it is very difficult to test all of them. And therefore, you will need a sample that needs to be as representative of all of the students enrolled in Asturias schools as possible. A distinction needs to be drawn between the theoretical sample, which is usually broader, and the final sample, on which the final tests will actually be conducted. The theoretical sample depends on the size of the population of reference, depends on the precision the analyst aims to achieve, and also depends on time and budget constraints. We then further narrow down the sample to get the final sample, which is, besides the theoretical sample, also based on inclusion and exclusion criteria, such as the age, gender, and administrative data. And these inclusion and exclusion criteria in an education setting could also be the educational program followed, prior grade repetition, etc. Imagine, for instance, that you want to test the treatment effect of a financial education program, but on students whose major is not necessarily economics or finance. And then this would be another inclusion criteria for a student to be included in your final sample. Dear participants, welcome to submodule 2.9, in which we will learn how to correctly randomize when setting up an RCT. For correct randomization, we need 3 criteria to be met, and we also have a practical advice. Let us start with the practical advice first. In theoretical analyses, scholars tend to model RCT situations with only one treatment group and one control group. However, for practical matters, for instance if the study is time constrained or space constrained or for safety reasons, you can also define more than one treatment and control group. A very important rule for randomization is that for each individual, the probability of being randomly assigned to the treatment group must be equal to the probability of being randomly assigned to the control group. Another important rule is that selection factors should be equal on average between the treatment group and the control group. Such selection factors could be personal characteristics, for instance, or prior grade repetition, the study track followed, etc. Finally, the allocation of an individual to a treatment or control group should not be influenced either by the participants or the analysts. Otherwise, this might create biases, and we will address biases in the following submodule. Dear participants, welcome to submodule 2.10, in which we will discuss the different degrees of information of randomized controlled trials and potential biases that might arise from these degrees of information. First of all, what is a degree of information? A degree of information basically answers the question, who knows the allocation? Who knows that a given individual has been allocated either to the treatment or the control group? In the context of a randomized controlled trial, there exist three different degrees of information. The first one is called open procedure and consists in the allocation procedure being common knowledge. This means that everyone, both the analysts and the participants, know which participant has been assigned to the treatment group and which participant has been assigned to the control group. Then we have single-blinded allocations, in which only the analysts know the allocation of each participant to the treatment or control group. And finally, double-blind allocations, in which neither the analysts nor the participants know the allocation of the participants. So the allocation is basically, for instance, defined by computer, and neither the analysts nor the participants get informed of the eventual allocation. Dear participants, welcome to submodule 2.11. After having discussed the different degrees of information, we will now more precisely discuss the biases that might arise from the different degrees of information. We will start with biases arising from open procedures. Before doing so, let's have a quick reminder that in open procedures, the allocation procedure is common knowledge, which means that both the analysts and the participants know who has been allocated to which group. The open procedure allocation makes it possible that some biases might occur. Note that these are potential biases. They do not occur for sure, but the open procedure allocation makes them possible. We first have the adverse reporting bias. If participants know their allocation, they might adapt their reporting to this knowledge. Furthermore, psychological effects might also emerge. If participants know that they are treated, could they then be cherry-picking evidence which confirms that their treatment is effective? Or put otherwise, if a participant believes that his treatment will be effective, they might start to cherry-pick evidence and only report evidence that actually confirm an effectiveness of a treatment, which creates to some extent a self-fulfilling prophecy. Dear participants, welcome to submodule 2.12, in which we will continue to learn how to set up an RCT and more precisely discuss biases in single and double-blinded allocations. Before discussing biases in single-blinded allocations, let's remind ourselves that in single-blinded allocations, only the analysts know to which group, meaning treatment or control group, each participant has been allocated. Potential biases that might then arise in single-blinded allocations are adverse reporting regarding the analysts, which means that the analysts might selectively report findings that support the treatment effect to show that their intervention had an impact, or compensatory guidance. Analysts, because they know who has been assigned to the control group, might start to additionally guide the control group, which might then weaken the treatment effect. In double-blinded allocations, neither the analysts nor the participants know which participant has been allocated to which group, and this actually minimizes the risk of adverse or biased reporting and preconceptions. Dear participants, welcome to submodule 2.13, in which we will learn about binary variables in regressions. In this and the following submodules, we will explore and potentially refresh some statistical knowledge that might be useful to better understand the measurement procedures of an RCT. Let us first define what binary variables are. Binary variables are variables which can take only two values, 0 or 1. 0 could be used to model a non-treated observation, an observation that did not benefit from the intervention, whereas a 1 could model a treated observation, an observation that benefited from the intervention. Therefore, a binary variable called treatment could be used to model whether an observation did or did not benefit from a given intervention. Let us continue with an intuitive introduction into regressions. A regression links an observed phenomenon to possible explanations. This observed phenomenon, which is usually the phenomenon we want to explain, is written y, while the possible explanations are captured by the variables which are noted x. If now we have one phenomenon we want to analyze, y, and all the possible explanations x, the impact that these possible explanations x will have on the observed phenomenon are captured by the betas. So the betas are to some extent the impact that the explanation has on explaining the observed outcome, the observed phenomenon. So if you have a huge beta, the respective explanation x might have a huge impact. If we have a small beta, the impact might be smaller. However, not every beta is significant. A non-significant beta means that we cannot be sure that this explanation is actually valid. We will come back to this later on. Finally, we have the small epsilon. The small epsilon captures everything that cannot be explained by the explanations we already have. Often we want this epsilon to capture as few things as possible. Let us now add a binary variable into this regression. By adding a binary variable, which we would note, let's say capital B, we introduce a binary condition for observation I at time t. For instance, we could define capital B as capturing whether student I was enrolled in a summer school in year t or not. And thus, the binary variable would take value 1 if student I indeed was enrolled at a summer school in time t, and value 0 if not. If we define the binary variable this way, beta binary becomes the impact of being enrolled at a summer school at time t. In this context, we see that beta binary is actually the impact of the binary condition on the observed outcome. So if we ask ourselves questions such as, what impact does it have to be enrolled at a summer school at, let's say, a student's grades? Beta binary would then tell us whether there is an impact, which means that if beta binary is significant, then there is an impact, and how big this impact actually is. So if we have a significant and huge beta binary, provided that we have taken the correct form of models, in this case, we know that there is a huge impact of being enrolled at a summer school on students' grades. Dear participants, welcome to submodule 2.14, in which we will continue to learn how to set up an RCT, and we will have a more precise look today on the two different types of difference that are relevant in an RCT setting. Let us have a look at the different points of observation in an RCT. What do we mean with that? With points of observations in an RCT, we mean the different moments in time on which we are able to observe things, to gather data. So actually this whole RCT starts from one big sample, which is the sample before the intervention not treated. Based on this sample, we will allocate a portion of the participants, often we attribute a half of the participants to a treatment group. And therefore, we actually get two groups of participants. A first group, which is the group before the intervention not treated, which will be equivalent to control group, and the group before the intervention will be treated, which will in the future become the treatment group. Now we intervene. After the intervention, we then have a treated treatment group from which we could also gather data. And based on this data, we will later on define or compute the effect, if there is an effect, of our intervention. Whereas the control group, or the group of participants before the intervention not treated, will just become the group after the intervention not treated, and thus constitute the counterfactual for our RCT analysis. Let us now return to the main aim of an RCT. A randomized controlled trial aims to quantify the impact of a treatment on a prior non-treated group compared to what would have happened if the treatment had not occurred. So if we have this graphical representation of a non-treated group, which transforms to some extent into a treated group, what actually interests us in an RCT is the process. We are interested in what happens during the treatment and which effect this treatment has on the group. In the case of an RCT, we are confronted to two different dimensions of impact. We first have a temporal impact of an RCT, so we have a comparison before the treatment versus after the treatment, and we have some kind of a treatment dimension. We compare the non-treated groups to the treated groups. Dear participants, welcome to submodule 2.15, in which we will continue to learn how to set up an RCT. And today we will have a closer look at the difference in differences approach that we already mentioned some submodules ago. As we discussed at the end of the last submodule, we actually do two kinds of comparisons in an RCT. On the one hand, we compare on a temporal basis. We compare before the treatment versus after the treatment. But on the other hand, we also compare the treated group with a non-treated group. So we compare both in a temporal dimension and in a treatment dimension. And the difference in differences allows to determine what occurred in the treatment group after the treatment. So a difference in differences actually combines these two dimensions in comparison. We can visually explain difference in differences through this table, in which you can find back actually the 4 points of observation we discussed last time. You have a beta 0, which stands for the control group before the treatment. You have beta 0 plus beta 2, which stands for the control group after the treatment. You have beta 0 plus beta 1, which stands for the treatment group before the treatment. And you have a treatment group after the treatment, which is captured by beta 0 plus beta 1 plus beta 2 plus beta 3. As you can see on this table, the only beta that only occurs in the treatment group after the treatment is beta 3. And beta 3, therefore, is the difference in differences. The effect that occurred only in the treatment group and only after the treatment. As we have learned, betas capture the impact. And in this case, beta 3 would capture the impact of our intervention, only if all the assumptions are met, of course. How we will set up this practically, that's what we will learn in the following. Dear participants, welcome to submodule 2.16, in which we will continue to learn how to set up an RCT, and today we will focus on difference in differences in regressions. So we will actually take what we've learned last time using our table and have a look at how we can actually get these results, because so far we have only discussed what the different betas mean, but we do not know yet how to get them. That's what we'll address today. Indeed, so far, we learned about binary variables. We distinguished between the temporal and treatment dimensions of impact. We learned which coefficients would matter in a regression. Now, let's use all of these elements to describe a regression used for difference in differences-based measurement. This would be an example of a regression which uses a difference in differences approach. After would be a time variable, taking value 1 if the observation was taken after the intervention and 0 otherwise. Treated is a treatment variable, which takes value 1 if the observed individual was in the treatment group. Now, let's reflect and think about what would happen in each of the 4 points of observations. If we have the control group before the treatment, then treatment would be equal to 0, after would be equal to 0, and therefore treatment times after would also be equal to 0, and we would only keep beta 0. If we have the control group but after the treatment, you would have beta 0, treatment would be equal to 0, but after would be equal to 1. Therefore, we would only keep beta 0 and beta 2, as treatment times after would also be equal to 0. If we have the treatment group, but before the treatment, we would have beta 0 plus beta 1. Why? Because after would be equal to 0, and therefore treatment times after would also be equal to 0. And then finally, if we have the treatment group after the treatment, then treatment is equal to 1, after is equal to 1, therefore treatment times after is also equal to 1, and we have beta 0 plus beta 1 plus beta 2 plus beta 3, which establishes why beta 3 captures the difference in differences. Of course, as in the regression we previously discussed, y would be the observed phenomenon for observation I at moment t, beta times x would be the other variables included in the regression. As we previously discussed, we want epsilon, so everything that cannot be explained by the explanations we have, to be as small as possible, and that's why we include so-called control variables. We want other variables to be in our regression to capture possible impacts if other explanations might have small impacts on the observed and analyzed phenomenon as well. Dear participants, welcome to submodule 2.17, in which we will have a small look on significance tests. In simplified terms, a variable is said to be significant when we can be sure at a given percentage that it influences an observed outcome. Therefore, if a variable is significant at a 90% threshold, we can be sure at 90% that a variable influences the analyzed outcome. If a variable is significant at a 95% threshold, we can be 95% sure that a variable influences the analyzed outcome. The same applies if the variable is significant at a 99% threshold. Then we can be 99% sure that the variable influences the analyzed outcome. Note that most studies use a 95% threshold. Let us use this knowledge to come back to our visual explanation of the difference in differences approach. As we have previously described, beta 3 is the difference in differences. Or beta 3 is the effect that occurred only in the treatment group after the treatment, and if all the assumptions are met, is therefore the effect of the treatment. So what we actually want to establish is not a huge beta 3, but a significant beta 3. Once beta 3 is significant, we can be sure that our intervention had an impact. Dear participants, welcome to submodule 2.18, in which we'll do a small case study on the impact of positive feedback on girls' self-concept in mathematics. This case study will be based on the article The Effect of Positive Feedback on Primary School Students' Academic Self-Concept, Gender Heterogeneity in a Light Touch Randomized Intervention by Tamas Keller, who found that positive feedback leads to an improvement of girls' self-concept in mathematics. In his study, Dr. Keller conducted the following randomization. Based on 1,253 students from grades 58, and based on a randomly generated number, each student got allocated either to the treatment group or the control group. Dr. Keller then uses the following empirical strategy. After first having asked students on their mathematics self-concept, he lets them write a grade-specific math test. If the student has been previously attributed to the treatment group, the student then gets random positive feedback, which was the following. You did an outstanding job on the math test. As your test score reflects your ability, you should be really proud of yourself as you are a bright and intelligent student. After either the random positive feedback for the treatment group or immediately after the math test for the control group, each group has to answer some self-concept questions in mathematics again, before continuing with some placebo questions. Dear participants, welcome to submodule 2.19, in which we will apply everything that we've learned so far to a case study. This case study will be based on the article The Effect of Financial Education on Students' Consumer Choices, Evidence from a Randomized Experiment, published by Professor Kenneth De Becker, Professor Christoph De Witte, and Professor Geert van Kampenhout, who found that traditional financial education does not automatically lead to a change in consumer choices. In their article, Professor De Becker and his colleagues focused on two different questions. The first one was whether the financial literacy course was effective, and the second one was whether the financial literacy course actually alters consumer choices. However, in this submodule, we will mainly focus on how Professor De Becker and his colleagues were able to determine whether the financial literacy course was indeed effective. This slide shows the timeline of the study conducted by Professor De Becker and his colleagues. This timeline is also a great illustration of the different pathways followed by the treatment and the control group. Whereas the treatment group followed a 4-hour course on financial education, the control group did not. Professor De Becker and his colleagues then used this regression to estimate the effectiveness of the financial literacy course. Dear participants, welcome to submodule 2.20, in which we will start to have a look at the ethical considerations behind RCTs. One fundamental document in research ethics is the Belmont Report, which requires the respect for person, justice, and beneficence. Let's have a look at what all these different aspects mentioned by the Belmont Report actually mean. The first aspect we want to discuss is the aspect respect for person, which requires that a participant enters voluntarily into the study, enters with adequate information into the study, and is not influenced into participating. Dear participants, welcome to submodule 2.21, in which we continue our discussions on ethical considerations linked with RCTs. Today, we will have a look at another basic principle of research ethics mentioned by the Belmont Report, namely the principle of beneficence. A study complies with this basic principle if a study creates no harm, respects the participants' decisions, and protects the participants from harm. Dear participants, welcome to submodule 2.22, in which we continue our discussions on ethical considerations in RCTs. Today we will discuss the remaining basic principle of research ethics, namely the principle of justice. A just study gives each participant an equal opportunity to participate. Vulnerable populations are only included or excluded based on their eligibility, but not based on the aspect that makes them vulnerable. There is no other exclusion due to barriers other than eligibility, which means that participants are not excluded for other factors than their eligibility. And finally, participants should not be included for their easy availability. A just study does not include prisoners, for example, only because they are easily available. Dear participants, welcome to submodule 2.23, in which we will discuss informed consent. In an RCT, participants are either allocated to the treatment or the control group, but actually both groups face risks. If we are in the treatment group, there is the risk of unwanted side effects, and if we are in the control group, there is a risk of missing a potentially beneficial treatment, and therefore, no matter which group, meaning treatment or control group, a participant is allocated to, they always face a risk. As participants always face a risk, they should sign a form of informed consent to participate in the RCT. By doing so, they acknowledge having been informed not only of this risk aspect, but also of all the other relevant aspects related to this study. Dear participants, welcome to submodule 2.24, in which we will continue our discussion on informed consent. As we have seen, the risks are not the only element participants should be informed of when signing an informed consent. Indeed, besides the risks, informed consent should also cover other aspects, such as the purpose of the study, the expected benefits, alternative procedures, procedures from data collection, the ability to withdraw from the study, the rights of the participants, privacy and confidentiality aspects, or the financial aspects of participation. On this slide, you can see all the sources that have been used to develop this second module. The effect team thanks you for having completed module 2. If there are any remaining questions, suggestions, etc. regarding this module, please feel free to contact Professor Dr. Christoph de Witte, who is the main coordinator of EFFECT and the director of the LEER research group at KU Leuven.